And we will run it on our Netronome Agilio cards, so we will get a bit of hands-on experience in doing that. Apologise, I see some people here who were at the OVS conference and even some people who actively contribute to OVS, so this lab might be a wee bit simple for these guys and people who know OVS, but hopefully for everyone else it'll give a bit of an experience of setting up a bridge, adding ports, sending some traffic, doing VM to VM connections, some of the basic rules in OVS, and if we get a chance at the end, conscious with time here, I'm going to show some of the firewalling capabilities, the stateful firewalling capabilities that are now available in Open vSwitch. So, the important slide, a few changes from the first lab here for anyone who wants to do it. So, well, before I start, if you go to the same URL, you can download the lab book for this under Lab 4 OVS. But we are going to have to change some of your server login cards. First of all, anyone who has SDK user 2, you can't use it for this lab. So please see one of the Netronome guys, and we will give you an SDK user 1 card. Please do not, if you have an SDK user 2 card, do not try and log in under SDK user 1, because someone else will be using that and things will get crazy. Also, if you have the card with 207.188.181.44 on it, can you please replace that for a new one, because it's died when we were reinstalling this. And then, I don't know if people are mainly using Macs or Linux or have PuTTY on their Windows machines. If you have a 207.188.181 address, well then we'll ask you to directly SSH into those machines from a Linux terminal, from your Mac terminal. However, if you have a 10.8 address, you're going to have to go through the VMs that we used in the first lab. So everything here will be done over SSH and in terminals. So if you've got a problem with that, if you prefer to use a VM and you don't have a 10.8 address, then we'll try and get a swap for you. Or if you prefer just to go through your normal OS, we'll try and get you a 207 address. So, any problems here, or everything good? So just before I continue on with some of the introduction stuff, this is the setup I'm going to use. So maybe for convenience, you can open 3 terminals to your server under SDK user 1. And, well, this is known in the lab. This is the way I'm going to display them. So maybe something similar. It will save us a bit of time later on. So I've just been informed that we're actually out of servers now, so if anyone else still needs one of these changes, we've one more, Mary has one. Everyone sorted? If not, please ask that you maybe work with someone. Okay, I'll continue on. I have a few slides here, but because we want to get started in the lab, I will try and get through them pretty quickly. I'm sure most people here know what OVS is, so I will not dwell too much on this. I suppose the main point here is, we can't really see it, but it's slightly highlighted in red, that to me, Open vSwitch, although it's got the word switch in the title, it's really more than a switch. Open vSwitch does a lot of stuff. So sometimes when you think switch, you think layer 2 switch and just simple MAC forwarding or whatever. We can do pretty much layer 2 to 4 here. They can do a lot of tunneling protocols, other activities like quality of service stuff, metering, all integrated. And hopefully we will get to show you some of the firewalling stuff that can now be done with OVS directly. Again, this is far from a complete list. So Agilio OVS is how Netronome really offload what is going on with standard OVS. And this diagram kind of depicts how we do that. So 3 layers. Our SmartNIC at the bottom, the OVS kernel and OVS user space. For this setup, we do kernel offload basically. So we offload the kernel data path in OVS. So really 3 routes a packet can take through the system. The first packet that comes in will probably not match in the SmartNIC. It will go to the kernel. Will probably not match in the kernel, and it will go to user space. If we've added our user space rules, we should get a match here, and the packet can complete the actions and go out of the system. Triggering that user space rule then writes a data path rule down to the kernel. So we will show examples of this throughout the lab and show exactly what we're offloading here. So another packet may come in, may miss on the SmartNIC and may match the kernel this time and egress the system. When we do this offload, or this data path rule to the kernel, it is also passed further down to the SmartNIC. So we can basically handle anything that can be handled in the kernel at the SmartNIC level. So hopefully when the rules are programmed through, the rest of the packets can come in and can simply match on the SmartNIC, apply the actions there and egress. So the lab setup, this is roughly what is going to go on each of your servers. We should have, hopefully, 2 VMs running already on the machine. And we have a physical port, P1 that you used in the first lab, that we can replay traffic into the system. All of these we will be, throughout the lab, connecting through OVS directly to our Netronome card. And we will add rules through the command line interface into OVS. These should filter down. We will try directing traffic through from physical ports to VMs, from VM to VM, and we'll play about a bit with that. So let's get going. Again, if you got the original URL, you can happily take the workbook and continue on and go through here. If not, you can follow on screen with me as I try to go through it. I'll try and highlight which commands you really need to call. Some of them are just to kind of display what's going on. If you don't work through them yourself, that's fine. You can see on screen. But as long as we do some of the key commands, we can still push traffic through the system. So we'll just start on point 2 actually. So first thing, OVS should be running on your system. If you want to, you can use OVS CTL and call something like version. That should give just information on some of the firmware we're applying. And you can see we're running in firewall mode, which will be useful for later on. The first command that I would really ask you to run is OVS vSCTL. vSCTL is an app supplied in standard OVS that allows us really to interface with the switches and configure the switches. So the first thing we do is OVS vCTL add bridge. So create a new switch and give it a name. We're going to call it BR0 here. You can call it what you want, but you will need to change the other rules throughout. And if we do OVS vSCTL show, we should see that we have created a bridge or an OVS switch, and this will really form the basis of our lab. So the second thing we're going to want to do, now that we have the bridge, is we're going to want to connect some ports to it. On the system, there should hopefully be a series of interfaces. We can see P1, which we'll use later. But I want to draw your attention to SDN/P, P0, P1. These correspond to the physical ports on the Netronome card. On down, we should see a lot of V.0.1.2. And these correspond to the VFs on the system that we can use for offload. So these are really representative net devs. In other words, if you kind of run TCP dump on these, you're not going to see all the traffic flowing through the system. You might see some of the fallback traffic, so some of the traffic that comes in and goes to OVS for processing, but you're not going to see all the traffic. However, if we apply these, they kind of act as a hook to the interfaces on the card. So when we offload rules that are connected with these, they will be offloaded to those particular ports on the card. Might be safer copying and pasting here. I will copy these over. These commands use, again, OVS vSCTL to really add ports to the system. So the first line here says SDN port 0 or P0, so that is the physical port 0, which we'll be using. We want to add that to our bridge B0, which we created previously. We also say OF port request equals to 1. So this is really requesting that we call this port 1. So on our OVS bridge now in user space anyway, SDN /P0 will be referred to as OpenFlow port 1. If we modify this slightly, if you take it out of your lab books, we want to use ports V0.2 and V0.3. We want to add them to the system too. These are really VFs that we have already bound to the two VMs that are hopefully running on your system. So we will use this to access the VMs directly from the card. And we will give them a request that they get numbers 2 and 3. So again, those port commands are very important to call if you want to continue with the lab. Some of these commands I'll just show you. You don't have to run them yourself, although you're more than free to. These are just highlighting now the setup of the bridge or the OVS switch as it stands. So you can see we have a bridge called BR0 and we have 3 interfaces connected to it: SDN, P0, V0.2 and V0.3. To add rules to the bridge, we'll be using a different app called OVS OFCTL. So that's really our user space interface here, where we can check some statistics in user space, add rules as we see. We can also do OVS OFCTL show BR0, so show what's going on in the bridge. And we should see that all our ports are listed here, and we'll see beside the interface name or the representative netdev name, we have a port number. So these are the port numbers that Open vSwitch now expects. So if we want to do anything, either match and say something coming in SDN V0.2, or we want to direct traffic to that, we just use the number port 2. So this should be hopefully down to the next section on our booklet. When we have this, we basically have a switch set up. We have our switch created, we have ports applied, and hopefully they will link. Now we want to add rules. Hopefully replay some traffic through. If you go into your book and you copy the following commands, this one just simply deletes flows that are already on the bridge. Sometimes default flows are added, so we'll just clear them for a wee bit of housekeeping. And we will add our own flow. So I think the flow itself is fairly explanatory. We want to just add a new rule to our bridge to say match on input port 1 and action output to port 2. So again, these correspond to our physical port, which is 1, and SDN V0.2, which is port 2. Again, if we do OVS OFCTL show or dump flows, sorry. BR0, so show all the flows we have installed in the bridge. We will see our output will be the flow we've just added. And some statistics about that: no traffic flowing at the minute, no packets through, no bytes through. Next, we want to gain access to one of our VMs. So, as I say, in a different terminal, we'll keep this open throughout. Just call the ARP command, and we should get a response, something similar to this, maybe not exactly. But we should see two IP addresses, 192.168.122. They may be 5.3, they may not, on the virtual bridge interface. If we check the MAC addresses, we've hard-coded these. The one ending in 01 corresponds to VM1, and the one ending in 02, as you might expect, corresponds to VM2. So from here, we can actually SSH into these VMs. For the first test, we will use VM1, which is a MAC address 0.1. In my case, 192.168.122.5.3. And password is Netronome if you log in as root. It should be in the lab book. And I hope the password is Netronome. And we should now have access to our VM1. This isn't a command that you need to run, but it's just something I'm going to run to show. Really, the output of this, our interesting line is here. Device 6003 is our Netronome card, and we can see that each one interface has been bound to this. So this is the VF interface linking direct to the Netronome card on the system. So at this stage, we are ready to try and hit this with some traffic. To make sure we're receiving traffic, we're going to run Tcp Dump on our VM. So you can filter for UDP traffic, that's what we're going to send. And we're going to run it on interface ETH1, which is, as I've just shown, is our NetDev corresponding to our Netronome card. May see some other packets get through here, but there's going to be traffic. So if we go back to our main switch terminal, you also have access, as you did in the first lab, to port P1. So this is really a second NIC that's on the card that is sort of looped back to the ports on the Netronome card. So now we're going to use TCP Replay to shoot some traffic out of this second NetDev, loop around and come back into the Netronome card. And as the rules showed earlier, hopefully this will match coming in port 1, what we find is our physical port, and go to port 2, which should be hooked to our VM that we're running TCP Dump on. Traffic is sent, and in the bottom left, traffic is received. So if we do now the command we ran previously, OVS OFCTL, dump flows, BR0, we should see that our stats have incremented. We've sent 100 packets through. They've all matched. They've all hit this rule, and as TCP Dump shows, they've all come out. So these really are the user space rules that we're doing here. So the first diagram I showed in the slide, that's kind of the top level. The first route a packet can take through. The rules then that are produced, the data path rules that filter down to the kernel and in turn filter down to our SmartNIC are slightly different. The data path rules themselves have a timeout, default timeout of about half a second. So they're quite hard to catch unless you do what I'm about to do and turn off the timeout. So again, this is maybe something, if you want to catch up, you don't need to do yourself. You can assume that it's happening on your system if you're getting traffic through, but I'm going to run here and just to highlight. So this command here should turn off our timeouts. And then if I run the traffic through again, it should get through to the VM. We should now have 200 packets through here, but this time our data path rules should not have timed out, so we can actually go and look at them. These are the rules that, as we say, have filtered down to the kernel and have in turn filtered down to the SmartNIC. So instead of OFCTL to interface with the user space stuff, we use DP, so data path CTL, and we just do dump flows. We don't need to reference a switch here. So these are our data path rules. The first one is, well, it's a drop rule. This is one that's been created by some of the other traffic we're seeing on the network here. So this isn't one that's created by matching a user space rule. So it's kind of a default. When we don't match user space rule, we create a drop. The second one should be the rule we've added. So there are slightly more fields added. This is a conversion from OVS, from user space to a data path rule. So we're matching an input port 2. Again, this doesn't correspond to the OVS ports we supplied. These are the data path ports. We're matching an Ethernet type here, so IPv4. And we're outputting to port 3. So we sent 100 packets through here that should have matched. We have received 80, which may seem a bit strange. So this is basically, I would have expected more, but what seems to have happened here is that 20 packets have passed into the system and gone to user space and been matched there and output before these rules have filtered down. So we've kind of missed the first 20 packets, but after that, the data path rules exist in the kernel and exist on the SmartNIC, and we can match the rest there. So again, because those rules are there now, if I send another 100 packets with the rules already installed, I would expect this value to go up to 180. So all of these packets can now match on the SmartNIC. Let's just check. And in the bottom rule, we can see, yes, we've gone up to 180. So before continuing, if anyone else has tried out that, I suggest you reset the timeout on the data path in case crazy stuff starts happening. And yeah, we should be on to our next section. Any questions on anything so far? Or should be straightforward. So in the first section, we basically matched an import and sent to an output. Probably not that useful unless you're just looking to do a bridge, a cut-through bridge or something. So now we're going to try and set up connectivity between the VM we've been using here and the second VM. So firstly, we want to access our second VM, and this is what the other terminal is for. This time it will correspond to the MAC address ending in 02. And we are in VM2. To make this more realistic, we're going to assign the ETH1, so the VF cut through on both, an IP address. So I'm using ifconfig. You can use whatever you like. On VM1, we'll assign ETH1. Make sure it's ETH1, not ETH0, or we'll kill SSH. 0 or 10.0.0.1. And on VM2, we'll assign ETH1 10.0.0.2. So now we'll add this new set of rules. Well, again, firstly we'll delete the rules we've already added and start afresh. And we will add these three rules, which I will explain in a minute. Bit quicker copying and pasting than typing out. So yeah, we've simply added three rules here. The top one, or the first one we've added, is matches an ICMP, and this time instead of matching on an import, we'll look more at the IP header, and we will match on a destination IP address. So hopefully these rules are set up. Anything going to 10.0.0.1, which we just assigned to one of the VMs, will be directed to OVS port 2. The following rule, anything going to .2 will go to port 3. And then the final rule we add is what's called a normal action. This really just kind of broadcasts the traffic to any port that's other than the port that came in. And we've set this to match an ARP traffic. So to get a ping to work as we're about to do, we'll need some ARP traffic. So this should be covered. So yeah, to show this working, I'm going to run a watch. So you can do this yourself, or you can view it on the screen. These are the three rules we've added, looking at OVS OFCTL. And now I'm going to try and do a ping between VM1 and VM2. Hopefully this will go across the Netronome card. We'll see some of our rules updating, and the pings will complete by making it to the other side. So from VM1, try and ping the other one, and we can see ping completing. And if we follow the rules, we can basically watch the packets go through the system, or go through the switch. So you can see 19 pings sent, 19 packets matching the top rule, 19 packets matching the second rule, and some ARP traffic. And just for conformance, we'll show that from VM2 to VM1, pings should also work in that direction. And again, the packets should be matching on the vSwitch. If we want to change that watch to see the data path rules, so the actual rules that are being offloaded to the kernel on the SmartNIC, we should be able to see them here too. Again, with half a second timeout, they come and go, but we should be able to see matches there. So that brings to an end the first main section of the lab, so really on the basic connectivity stuff. The next section is some new stuff really that's been added to OVS as of, well, 2.6 is very recently out, but this was added in 2.5, and it's really the ability to do some stateful firewalling. So for those who know Linux and know the Linux kernel, it really interfaces the Linux kernel connection tracking module to try and add states to these flows, and to try and match based on state information of a packet, so how the packet is within its own 5-tuple flow, and use that information to try and make decisions. In this simple test, we're just going to expand what we were doing with the ping between the two VMs. And we're going to concentrate really on two states here. So new and established as really the basis for stateful firewalling. If a packet is new, that suggests that it's setting up a new flow. It's the first packet seen in TCP terms. It's the SIG flag. and established, meaning that this packet is part of an already formed flow. And again, that information is very useful when making certainly a security decision about the packet. So again, we will start by deleting the flows that are already there. And copying in these new flows. Just bear with me while I copy them, and then I will explain them. Okay, so everyone else up to date? We're actually ahead of schedule here, I think. So connection tracking within OVS is both an action and a match field, which maybe seems a bit strange when you say it. But as a packet comes into OVS or comes in to our Netronome card, there's no state known about that packet. All we have is the packet information itself, the header fields, and the input port and whatever else may be associated with it. So to actually do, or to gather this state information and to do connection tracking, or contract as it's known, we need to actually call this as an action. So the top rule basically says the match and connection state not tracked. So this is to say we don't know any state information here. This is a new packet entering the system. So irrelevant of what port it comes in, if it hasn't been tracked yet, our action here is to send to contract, which is this CT, and commit, meaning to store that entry in the connection tracking table, and table equals 0. Table equals 0 basically means once we send this packet to contract, and once we do a 5-tuple lookup, gather some state information about this, then send this back to table 0. So recirculate this packet. Meaning the packet basically goes through Open vSwitch twice. The first time it hits, it's sent to contract, it gets a state information, it goes back into the system. This time, the state information is part of the packet key. It's metadata included with the packet. And now, because we have this state information, we can start matching on it. So the next rule will be an example of that. Now what we're matching on is the state new and tracked, meaning that the packet has state information and what the state is. We can now match as well on an IP address of one of our VMs and do an action. We then have another match new in the opposite direction, so for 10.1, this time it's going to be a drop. I'll explain that in a minute. And finally, 2 more rules that match an established state, so packets that are actually part of an already established connection. And then we have our ARP packets just handled as normal. So the setup we're trying to do here is, well, it's basically a simple example of a stateful firewall. Here, VM1 is, say, our internal network, for example. It's good. VM2 is the outside world. It may be bad. So in theory here, the rules say that any packet, in this case we're just going to do it with pings, that or any connection, shall I say, that started from VM1 to the outside world, well then packets can flow in both directions. However, if the connection is established from VM2, or the outside world in this case, we'll then drop that packet that's starting the connection, and any other connections from that attempt to be sent, drop them as well. So we're really setting up a firewall saying, in our internal network, we can communicate with the outside world, but the outside world can't communicate with us unless we specifically request that. So, to see the packets going through again, I will run a watch on this. We'll try to ping from VM1 to VM2. And hopefully the pings will work. So we've set 7 pings here. The first rule, we've got 14 matches. This corresponds to the pings request and response. So everything's hitting this top rule and being sent to contract. We have 1 match on the state new, which is, for contract purposes, by the way, all of these pings are considered part of the same flow, as it were. We match once in new, so the first packet that's initializing the connection. We don't have a match on the third flow, as nothing's trying to connect in the other direction. And we should have matches for both directions, 6 and 7, unestablished. So when flows are established, they're allowed to travel both ways. This time, if we try to do a ping from VM2 to VM1, it shouldn't work. We should see everything hitting this drop rule. Sorry. Yep. So everything is being dropped. And if you've done that, you've basically added, what, 5 or 6 rules in OVS which have been offloaded to our SmartNIC that can create, basically a simple stateful firewall. And I think we have 5 minutes left. If there's any questions around this, or if people want to finish off. Everyone good? Did it work? Yeah. Yeah. So this is to do with the state. So kind of forget about the top rule. It's just telling everything that comes in, go and get the state information. So when we send a request from VM1 to VM2, the first packet is going to be new. So it's going to have state new. It's setting up a new connection. And we added a rule here to say if the state is new, and if the destination is VM2, we'll then output the rest of the pings that continue in that flow can match these 2 rules happily because they are part of an established connection. So if they're going to 10.0.0.1, go out 2, 10.0.0.2, go out port 3. However, in the other direction, we have this rule that says if the state is new and it's going to our trusted network, in this case, we're saying is VM1, we'll then drop the packet. Don't let that pass the firewall. Yep. So none. That's what this rule does. So there's none. So the first rule says match a packet. It just says match a packet that doesn't have state information. So this is internal to Open vSwitch. It It's not on the packet when it comes in. It's not on the packet when it leaves. This is internal state information. First rule says go to contract, so this CT bit here, and table 0 means insert this back in, do a lookup on table 0, insert it back in. So when we do this CT, we go do the packet lookup on 5 tuple. We also do, it gets more advanced to do a lot of TCP window size checking, sequence numbers and stuff. We then kind of append this metadata to the packet. So when the packet comes in, well, come in is maybe wrong, but go stay in the system, but just be matched again. It has this metadata. So this metadata now exists. And on this second pass-through, we can now match on it. So we can say it's new, it's established. And yeah, there's a lot of other information we can add. This is just a simple example in 45 minutes. Okay, I think that's 4 o'clock. Perfect. Thank you.